Okay. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. The next position we had was 2 to the power of 3, and then 2 to the power of 4. And it keeps going on like this for however many digits you have, right? So once you get a practice of, converting, you won't need to write these 2 in the powers. You'll just know that the first position is 0, 1, 2, 4, 8, and then so on, 16, 32. It just keeps going as you increase this power. So instead of dividing by 2, another thing you could do to convert 17 is that you'll notice that these positions, let me write down from 16, okay? 1, 2, 4, 8, and 16, and then we have, let's write down to 32, okay? I need 17. So the highest number I can get first is this, using this, right? So 1, if I put a 1 in the position of 16, and if I put a 1 in the position of 1, that would mean 16, because this is using 16 and 1. So 16 plus 1 is equals to 17. I'll just write 16 and 1 in the position of 16 and 1, and then the rest of the places have 0 in it. And since this place is at the left-hand side and there's no other 1 after that, I could just ignore this. So it'd be 1, 0, 0, 0, 1. Okay?
Yeah.
All right. So this is another way you can convert. I personally like using this one better, since in this one you have to have a lot of guessing and involved and stuff. So great. Okay, now we've done denary to binary. Let's try doing binary to hexadecimal. Okay. So what is hexadecimal? Hexadecimal, let me take a new page. Right, so hexadecimal is, again, it is a kind of a short form for binary. And how is it a short form? So the way this works is that it'll take some binary number. Let me try converting binary to hex. For hexadecimal, the first thing you should know is that its language has 0 till 9, and then after 9, it goes from A to F. Okay, and the way this is converted is that let's take a random binary number, for example, 110101. Okay, now I want to convert this to hexadecimal. I'm going to do this by, first of all, I'm going to look from the right to the left again, as I would with binary, and then I'm going to split this binary number into groups of 4. Okay, so this is my first number, and then second, 2, 3, 4, and then I'm going to break it off here. Okay, so I have one group of 4, and then this place has only 2 in it, right? So that means it's not a group of 4. I'm just going to add, why is this other color again? I'm just going to add 2 more zeros at the left to make it a group of 4. And adding zeros at the left of this any complete binary number doesn't actually matter, because it doesn't count for anything, right? You noticed how we were converting from binary to denary. We weren't counting the values that it had in those 0th positions, right?
Yes.
So that's why I could just add 2 zeros here and then convert this. So let me convert this. Now I'm going to convert this group the normal way I would a binary to denary number. Now this position has 2 to the power of 0 plus 2 to the power of 1, which it won't count. So move on to the next one, 2 to the power of 2, which does count because it has 1 position, and then 0 again, so that doesn't count. So this is 1 plus 4, which is equals to 5. Now 5 is a part of our hexadecimal language. So I'm just going to leave 5 as it is, and then let's convert this to denary. Now this to denary will be by, let me choose a different thing. So this is denary. This is the first position, which is 2 to the power of 0, which I will add because there's a 1 in this place. And then I have 2 to the power of 1, which does count because it has a 1 in its place. And then these two, again, it won't count because it has zeros. Now, these two are added, which is equals to 1 plus 2, right? And then this is 3.
Yeah.
Right? So this is 3. And again, 3 is a part of our hexadecimal language because, again, hexadecimal said it's 0 till 9. And 3 does come under 0 till 9. So it's 3 and 5. Now, the hexadecimal language of of 110101 is, in hex, it's 35. Okay. Now, another thing you need to know is that they also have A's and A till F. Now, when does this come? This comes when I have, for example, instead I had another hexadecimal number. Let's take another example. Let me actually do this again. I have another number, a hexadecimal number. Let's say I have 1101 and 1111. Actually, I divided it first already. Let's say there's another 0 here and 1 here. Okay. Now I want to convert this to hex. What am I going to do first? I'm going to look from the right to the left and break it into groups of 4, right?
Yes.
So 1, 2, 3, 4, and then I'll break one here, and then 1, 2, 3, 4. I'll break another one here, and then 1, 2. I'll add 2 more zeros at the left, and this is another group of 4. So let's convert this part first. So as it has all ones, that means I'm going to add all these positions, right? Because there's no 0 here. So this is 2 to the power of 0. So 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3. And this is equals to 1 plus 2 plus 4 plus 8. Again, that same position format, 1, 2, 4, 8. And then this added up is supposed to be 16, if I'm not, or 15. 8, 9, 10, 11, 12, 13, 14, 15. It's 15. Now 15 does not exist in our hexadecimal language. As we said, it's only up to 9, and then the alphabets till F start. So actually what this means is that A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. Now this 1111 is the maximum number you could have. In your hexadecimal values, right? Because this is the maximum number of ones you can have in a possible group of 4, right?
Yes.
So that means here I have 15. Which is represented by F in hexadecimal. So therefore, I'll write F here. And now let's look at the next group. The next group is 1101. So I'll just choose another color for this. 1101. The first position we have is 2 to the power of 0. So 2 to the power of 0 plus 2 to the power of 1 does not count because it's 0. And then 2 to the power of 2, 2 to the power of 2 plus 2 to the power of 3. And this is
1 plus 4 plus 8.
so this will add it up. It will be
13.
yeah. Now 13 in hexadecimal means D. So I will write D for this here, for the second group. Now I'm going to move on to this one. Let's take this last group. Now 2 to the power of 0, again, it does not count because it has 0 in it. The next thing we have is 1, 2 to the power of 1. So we have 2 to the power of 1, and the rest are 0, so again, they won't count. And I don't even need to count them because there's nothing else after this. So 2 to the power of 1 is equal to 2. The last thing we have is 2. So this is my final hexadecimal conversion. Sorry. This is my final hexadecimal conversion value for 10110111. Okay?
Okay.
All right. All right. Do you have any questions?
So far, no.
Okay. All right. So the next thing we'll do is let's try converting this back to binary. I take a new page. We have 2DF. Let's try converting that back to binary. Hex to binary. So 2DF. We have these three these three digits here or positions that we need to convert. So we already know that hex uses groups of 4, right? So that
Yes.
means F here is going to be represented by some 4-digit binary number, and then D is going to be represented by some four position binary number, and then 2 is also going to be represented by some 4-digit binary number. So let's try converting that. We have a total of 3 groups. So let's try converting this. So F, we know that F is equals to 15, right?
Yes.
Now we have to convert 15 from denary to binary. Now we're going to convert this 15. 15 divided by 2 is
7.5. So 7 and then 1.
yeah. And then
3.5. So 3 and 1. 1.5 and 1. And point and 0 and 1.
and 0 and 1. Yeah. So we have this group of 4. And I'm going to read it from the bottom to the top. In this, it doesn't matter because all of them are already 1s, but it's better to have that practice. Otherwise, you might make a mistake later. So 1, 1, 1, 1. Now we've done F. Let's try converting D. So we know that D is A, B, C, D. So it's the 4th one. So that's 10, 11, 12, 13. So D is equals to 13. Let's try converting 13. First one will be,
Is 6 and 1.
yeah.
3 and 0. And 1 and 1. And 0 and 1.
So reading this again from the bottom to the top is 1, 1, 0, 1. And then we have 2. 2 is just, you don't have to convert this to denary anymore because it's already in denary. So 2 to binary is 2 divided by 2, which is 0. And then 2 divided by 2 again, 2 divided by 2 is 1. And then 1 divided by 2 again is 0.5. So we have 1, 0 again, like this. It's going to be 1, 0. So 2df is equals to 1, 0, 1, 1, 0, 1, 1, 1, 1. Now this is the same answer that we got. It's the same answer as we got up here. Sorry, up here. As this. Okay?
Yeah.
All right, do you have any questions so far?
No.
All right. Now we have done, I'm pretty sure all of them now. Okay, let's go back to the textbook. We've converted binary. These are some questions that I'm gonna give like some of these for you to solve as well, so we can get a good practice of it. This is the conversion that I talked about, remainder 1 and all of this. Okay, the next thing we're going to talk about is the measurement of size and storage in computer memory. So this, do you play games?
I used to. Now I don't.
Okay, but do you know how every game or every software, any application, they all have a specific memory location that you need, a storage space that you need to be downloaded or used in any way, right?
Yes.
So this is in different kinds, like the way we have kilograms and grams and weight of any form, we also have storage in kilobytes, megabyte, gigabyte, terabyte, and petabyte. Okay, these are the main ones that we're going to use. And as you can see here, there are these 5. The first one is 1 kilobyte. So what is a byte? A byte is basically 8 bits. It consists of 8 bits. Now, these bits are, again, they're binary language. So they're zeros and ones. Now, let me draw here. So we had any number, like any binary number, right? This means like
Yeah.
this binary number shows that I have 4 bits because they're 4 certain bits. Instead of saying 4 digits, I will say that this is a binary number that consists of 4 bits. And if I had 8 of these bits, if I had, let's say if I had like 4 more here, these are 8 bits. And when 8 bits are together, this makes 1 byte. Okay?
Okay.
Right? And then 4 bits, if I had just 4 bits, it's known as one nibble.
Okay.
Okay. And similarly, if I keep increasing this, it keeps getting bigger. And sometimes and oftentimes you have a really large storage, like this first one, which is 1 kilobyte. 1 kilobyte, and we also know that kilo means 1,000, right? So
Yeah.
1,000 bytes make up 1 kilobyte. The KB is 1,000 bytes. Okay. And here you can see it says 1024. So they called it kilobyte just as a general representation. And normally when you're making calculations and like problem solving, you're going to use 1,000 and not 1024 so that you can easily solve it. And I'm not sure if now in IB you're allowed to use calculators, but if you aren't, then that is the way we used to solve these questions. Okay, so the next position that we have, okay, so to the power of 10, to the power of 10 is your number of bits inside a kilobyte. So yeah, and then as you go down, you'll see that these are larger in storage. And
Yeah.
these larger storage means that every single number of bits is increasing from the 2th power. So the first one is 1 kilobyte, which had to the power of 10. The second one is 1 megabyte, which has to the power of 20, and then to the power of 30, 40, 50. The first one again, 1 KB, MB, GB, TB, and PB. Okay,
Yep.
all right. Now let's go down a bit. Here they said the same thing. 1 kilobyte has 1,000 bytes, 1 megabyte, 1 million bytes, and it keeps increasing that way. All right. These are just the conversions that we just did. Okay. All right. This is another conversion table that they made for binary, hexa, and denary all in one table from 0 till 15. Okay.
Okay. I mean,
All right. Can you try converting this 45A? Let me write it down here. 45A to binary. This is the first question. I'll write down a few more here. Let's say 25C and 10F CAB. Okay. All of these, you need to try converting all of these to binary.
these are in hex, right?
Yes, they're all in hexadecimal.
the numbers before the letters are in denary, right?
Yeah, yeah.
Okay. I got the answer for the first one, but I don't know if it's correct.
What's your answer?
Zero, one, oh, from left to right. You have to read it
Yeah,
from left to right.
yeah.
Oh, from right to left.
And
From
when you're
here
reading
to.
the answer out, you're gonna be reading it from the left to the right, like normal
So
English.
my,
It's fine.
so my left or your left?
It's the same.
Okay, 0 1 0 0 1 0 1 1 0 1 0.
Yep, it's correct.